Okay. Hi, everybody. Today we continue a discussion of problems in electrostatics and in direct current. So I would like to start. I would like to start from problem 467. 467 says resistances R1 and R2 are connected in series. So we have two resistors, R1, R2, and these resistors are connected in series. Each resistor is 60 ohms. The potential difference between points A and B, that is point A and point B, the potential difference is given, it's 120 volts. Find the reading of a voltmeter connected to points C and D. So we connect a voltmeter here to these points. And we need to calculate, we need to find the readings of this voltmeter if it's connected to points C and D, and if its internal resistance is given. The internal resistance R of its voltmeter is given as 120 ohms. So we have to find the readings of this voltmeter, and the readings, I will denote the readings by capital V. We have to find this, the magnitude, the value of the readings of this voltmeter. So what happens in this problem? The readings of a voltmeter will certainly be equal to the potential difference between points C and D. So we can immediately write down that this will be just the potential difference between points C and D. That is potential of point C minus potential point D. And this potential difference between these 2 points will be equal, according to the Ohm's law, to the product of total current, which is here in this circuit, times the resistance between points C and D. And the resistance between the 2 points will consist not only of the resistance of R2, but also of the resistance of the voltmeter, which is connected in parallel to the R2. So the resistance between points C and D can be found according to the formula which we have derived. It will be R2, the internal resistance of voltmeter, R2 plus the internal resistance of voltmeter, as the resistance of 2 resistors connected in parallel, the total resistance between points C and D. Okay, we have found this quantity, and now we need to find the total current which will be in this circuit, and the total current, again according to the Ohm's law, will be directly proportional to the potential difference between points A and B, which is given in this problem, potential difference, and inversely proportional to the total resistance of this circuit. And the total resistance will consist of 2 resistances. First, it's R1, and then the resistance between points C and D, which we have just calculated. And these two resistances are connected in series, so the total resistance between these 2 points will be just the sum of these two resistances, R1 plus RCD. So we may continue the first line, the formulas in the first line of our equations. In order to find the readings of the voltmeter, we may continue these formulas by substituting the current, this expression for the total electric current, and that will be U divided by R1 plus RCD and multiplied by RCD. So everything is given in the problem to conclude calculations. The total potential difference between points A and B is given, the resistance R1 is given, and the resistance RCD can be calculated because all the quantities in this formula are given in the problem. So it would be easier to carry out the calculations probably by dividing numerator and denominator of this formula by RCD, and then we obtain such an expression, plus 1. And then we may probably calculate this expression, which will be 60 volts times 60 ohms times 120 ohms divided by the sum of these two quantities, that is 180. Well, to carry out these calculations, I will make some cancellations. We cancel, we divide by 10, and then we can divide by 6. 1 unit remains here and 3 will be here, so the answer will be 120 divided by 3, that will be 40. And so in this formula we obtain U is given as 120 volts, and here we will have R1, that is 60, divided by RCD, which we have estimated as 40 plus 1. So that will be 1.2 or 1.5, and the denominator will be 2.5. So the answer is easily obtained from here. I will put it as approximately 5. Approximately 50, because this is a decimal point, volts. So if we have two identical resistors, R1 and R2, which are equal, each equal to 60 ohms, two identical resistors, and the total voltage of 120 volts at first sight seems to be equally divided by these two resistors, and so between points C and D the potential difference here must be just half of the potential difference applied to the total circuit, just 60 volts. But anyway, this will be not true. The potential difference here will be not 60 volts, but will be 50, about 50, smaller, because the voltmeter has some internal resistance. There are some questions. I will answer this question a little bit later during this lecture. This is This is what I plan to do, but not right away. So in this particular situation, very simple situation, when we have two equal resistors, and the potential difference applied, the voltage applied to these two resistors must, according to our intuition, be divided by half. So each resistor should have potential difference 60 volts, 60 here and 60 here. Total potential difference will be 120. But anyway, the situation is changed if we connect a voltmeter to measure the potential difference here, and the voltmeter internal resistance is comparable to the resistance on which we try to measure the potential difference. So when the voltmeter will not influence the results of measurement, well, it can be seen from here that if the internal resistance of the voltmeter is much larger than the resistance R2, then R2 can be neglected here in denominator. Forget about R2 here. And then internal resistance of voltmeter will cancel. And then the resistance between these 2 points, RCD, will be just equal to R2. And then the voltmeter will not influence the measured potential difference. So to have a reliable measurement which is not influenced by the voltmeter itself, we must take such a voltmeter whose internal resistance is much larger than the resistance connected to the voltmeter in parallel when we try to measure the potential difference. So if the internal resistance of voltmeter is comparable to R2, and in this formula R2 cannot be neglected, then the voltmeter will introduce considerable influence on the measured potential difference. And the next problem I would like to consider will be 466. Yeah, 466. Let it be on another part of the blackboard. Problem 466. Find the resistance of a wire cube when it is connected to a circuit between points A and B. So we have a cube made of wire. Well, let me draw a cube. Does it look like a cube? Approximately so. And we connect the cube to the terminals A and B, to the external circuit. And we need to calculate the resistance of this cube, the total resistance of this cube, if each wire section has a given resistance. So this wire section has a resistance of R, and this is also the same, and this is the same, and etc. Each side of the cube, or every edge of the cube, has a given resistance, and all the resistances are the same. Every edge of the cube has resistance R small, which is given here. R small is given. So we need to find the resistance of this cube if we measure the resistance between points A and B. How can we calculate the resistance of such a complicated circuit? Well, looking at this circuit, we understand that we have neither parallel nor series connection of resistors, and connection is more complicated. But this complicated connection can be simplified. It can be reduced to something more simple if we recall that a cube has some symmetry. And the symmetry which is important here is that of symmetry about rotation, a symmetry with respect to rotation. So let's designate this point as point 1 and this point as point 2 and that point as point 3. So I draw your attention to 3 vertices of this cube. 3 vertices. What is particular about these vertices? Each of these points is separated from point A by just one edge, but just one resistance R. This is one edge of the cube, and this is one edge, and this is certainly one edge. So we have 3 vertices of the cube, 3 points, 1, 2, 3, which are in the same relationship to point A. And what is more important is that if we rotate this cube about the axis which goes through point A and point B, we rotate this cube, rotate in such a way that point 1 goes to point 2, and point 2 goes to point 3, and point 3 goes to point 1. So 1 goes to point 2, and point 2 goes to point 3, and 3 goes to point 1. That will be a rotation, well, about this axis. If we rotate by 120 degrees, which is 1/3 of the total revolution of 360 degrees, just by 1/3, then point 1 will go to position of point 2, and point 2 will shift to a position of point 3, and point 3 will be found in the position of point 1. The cube will coincide with itself after such rotation, and so we understand after that points 1, 2, and 3 are in absolutely identical position here in the cube, so that the electrical potential of these 3 points is the same. Must be the same because of the symmetry of this figure. If this is so, then we can connect points 1, 2, and 3 by a wire, and this wire will change nothing because there will be no current in this wire connecting points 1 and 3, for example, or 1 or 2. There will be no current, no electric current through these wires, because the potential difference between these 3 points is 0. All the 3 points are at the same electric potential. Potential difference between them is 0. So actually this is a single point. If the potential difference is the same, we can connect all these points, and then the 3 edges which I discussed before will be connected in parallel to one another. So this is the point A, the vertex A of this cube, and the 3 edges which go out of point A are actually connected in parallel, because if we connect points 1, 2, and 3 by a wire, this is the wire, then there will be no current in this wire, because all these points are at the same potential. And then the same thing is true related to other 3 vertices which are closer to point B, this one and this one, and which one, and this one. Another 3 vertices which are closer to point B, they will also represent 3 resistors connected in parallel, because the potential at these points is the same. The electric potential is the same. So at the other side of the cube, closer to point B, we will have the same circuit, the same connection of resistors, and this is point B. And what is in between? In between we will have another 6 edges of the cube, which will be connected in parallel. The remaining 6 edges, 1, 2, 3, 4, 5, and the remaining 1, 6. So this is an equivalent scheme of the cube whose edges have equal resistances. And each piece resistance is R. Each piece resistance is R. And we have to calculate the resistance of this connection. So the first section will have a resistance R divided by 3, because 3 identical resistors are connected in parallel. Another section will have resistance R divided by 6, because 6 identical resistors are connected in parallel. And then again, this section will have resistance R divided by 3. And so the total resistance between points A and B, the total resistance which we have to find, will be just the sum of these the resistances of these 3 sections. Because I remind you, this is just one point in the circuit. This is one point in the circuit. So all this is what? 2R over 6 plus R over 6 plus 2R over 6. That will be 2 plus 2 plus 1, 5. R over 6. That is the final resistance which we have found here. That will be 5 small R over 6. That is the answer, the resistance between points A and B of the cube. And points A and B are the opposite vertices located along the cube diagonal from point A to B. Opposite vertices of the cube. The resistance between these two opposite vertices will be 5 over 6 times R, where R is the resistance of a single edge. So in this problem, it was important to use properties of symmetry of this figure. These considerations of symmetry allow us to understand that potential difference between these 3 points, 1, 2, 3, is 0. All these points are at the same potential, and that is why we can connect them by a wire, and that is actually a single point in the circuit. So the considerations of symmetry allow us to modify this figure into an equivalent scheme. The original or the initial complicated scheme, which is neither parallel nor series connection of resistors, this initial complicated scheme can be simplified and can be reduced to an equivalent scheme. And why is it possible? Because the original scheme has some symmetry. And due to this symmetry, which turns out to be very important, the considerations of symmetry are always very important in physics. And in this simple situation, the symmetry allows one to calculate easily the resistance of this figure. So the next problem we will consider is 470. Yes. So problem 470. There is a circuit given in this problem, and the circuit is this. many repeating cells, many identical cells. And I will show the final cell which can be connected to this circuit. The final cell, and all these resistors are identical. All of them have the same, all resistors have the same resistance. All resistors are identical. All but the last one here. Between points, between the very last resistor is different, and we need to find it. And I will denote this resistance as X, and we have to find this X on condition that. So what should the resistor X be, so that the resistance of the entire circuits between points A and B does not depend on the number of elementary cells. So the resistance between points A and B does not depend on the number of elementary cells, does not depend on the length of this circuit. So it's constant. We can connect another cell here, and the resistance between points A and B will not change. And on this condition we have to find what should be this last resistance X, such that if we add more elements to this circuit, and there are many such identical cells, there may be 20 or 50 or 100 and so on, a large number of identical cells. So this may be very long picture, but all of them are identical, and we need to calculate X such that connecting it to the cell, to the circuit, will not change the overall total resistance between points A and B. So, how can we solve this problem, which includes infinite, practically unknown number of identical cells, which may be very large, 1,000, 2,000, no, or just 3 or 5 identical cells. We know that this resistance R, resistance X of the last resistor, should be chosen such that the total resistance does not depend on the number of cells in this circuit. So when this will be true, when this resistance between these points will not depend on attaching more cells here. It will happen when after attaching this last cell, the resistance between these 2 points will be the same as the resistance X. It means that if we attach here, if we connect here the last cell, then the resistance here will be equal to X. It means that nothing has changed in this circuit. If the last resistance was X, if the last resistance here was X, and if we attach another circuit, another element here, so that this resistance is R and X is here, then nothing changed. Nothing changed. The resistance between these 2 points does not change. If the resistance between these 2 points does not change upon connecting another cell, then the resistance between these 2 points also will not change, and we will satisfy the condition of the problem. So what we have to do is just to calculate the resistance of this remaining circuit here. The resistance of this remaining circuit must be equal to X, and that is the condition that when we attach another cell here with the final resistance X, then nothing changed. Nothing changes. No, the resistance of the circuit does not change. So the resistance of this circuit must be X, and it can be calculated easily because it's a parallel connection of one resistance and another 3 resistances. So in parallel connection, we will have such a condition that 1 over the total resistance here equals 1 over R, the first resistor connected in parallel, plus the second resistor, that is 1 over 2R plus X. So these 3 resistors are connected in series, and so the total resistance of this branch of the circuit will be just 2R, 2 resistances of these 2 resistance plus resistor X, which are connected in series, and so their resistance is just the sum of all 3 resistances. And so the total resistance between these 2 points will be calculated as the resistance of the resistors connected in parallel. The first one in parallel, the first parallel branch is just R, and the second parallel branch is the last branch in this cell, and so the total resistance of these 2 parts connected in parallel should be equal to X, because this is the condition of the problem. And so we need to find X from this equation. This is not a complicated problem, so we may write it here, we may put it in this way. That will be R times 2R plus X, and that will be 2R plus X plus R, so that will be 3R plus X. And then from this equation we find that 3R plus X times X, if we multiply by X, equals R times 2R plus X. So here from this equation I find this expression, I come to this equation. And if we open the brackets, then we find here X squared plus 3RX equals 2R squared plus RX. So these terms can be simplified, and finally we get this quadratic equation, which is 3RX minus RX. That will give us 2RX minus 2R squared equals 0. And from here we can find X, which will be minus this coefficient if we take minus, actually we must take one, we may take both signs, plus minus, but if we take minus, we obviously obtain negative value for a resistance, which is unphysical. We have to ignore this negative value. It's unphysical. We must take only positive value for the resistance. And so, yes, that will be sorry, that is just half of this coefficient, plus R squared minus this coefficient, that will be plus 2R squared. So that will be minus R plus R and square root of 3. So X can finally be written as R times square root of 3 minus 1. That is, we found the resistance of this last resistor such that connecting another cell here, another portion of this cell will not change the resistance between points A and B. That is the answer to this problem. We have found this resistance, which must be just square root of 3, which is approximately 1.7 minus 1. That is approximately 0.7 times capital R. That's the answer to this problem. If we choose such a resistance in this scheme, then attaching another cell will not change the resistance at between points A and B. Well, I would like to discuss the solution of another problem, 473. Problem 473, which says that we have a charge Q is put on two identical plane capacitors connected in parallel. So we have two identical plane capacitors connected in parallel. If they are identical, then they have the same capacitance. Two identical plane capacitors connected in parallel. And charge Q is put on the upper conductor, on the upper part of the scheme. So we put here charge Q. It will obviously divide it into two equal parts. So plus Q over 2 will be here, and plus Q over 2 will be here. On this plate of capacitor and on this plate, we will have equal charges because total charge plus Q is put on the upper side of the scheme. At the moment of time t equals 0, the distance between the plates of the first capacitor begins to increase. So we have the distance between the plates, and the distance turns out to be a function of time, and as a function of time, it begins to increase uniformly according to the law d0 plus vt. So this is the distance between d between the plates of the first capacitor. And the distance between the plates of the second capacitor starts to decrease uniformly. So again we have the distance d2 between the plates of the second capacitor. And this distance at the time t equals 0 also begins to decrease uniformly according to such law, which is given. This law is given. Neglecting the resistance of the feeding wires, find the intensity of the current and the circuit in the circuit when the plates of the capacitor move. So the plates of the first capacitor start moving, and the distance between them is increasing according to a given law. And the distance between the plates of the second capacitor start decreasing, so the plates start to move to each other according to another law which is given in this problem. And we have to find we have to find the current which will flow in this, the current which will be found here flowing in this wire. While the plates of the capacitors move, there should be some wire, there should be some current flowing in this wire. Why? Because first of all, we have to identify the problem. We have to investigate or analyze why there should be a current. Why? Because the charges on each capacitor will change, and also the capacitances will change of each capacitor. So we know that the potential difference between these two points between the plates of both capacitors will remain the same, but it will change also. The potential difference between these points, that is the potential difference U between these points, between upper and lower plates of the capacitor, this potential difference will be a function of time. It will be a function of time. It will change in time. But it will be the same for the first capacitor and the second capacitor. It will be the same. And the potential difference on the plates of the first capacitor, according to the definition, to a definition of capacitance, is what? Is the charge on the first capacitor divided by the capacitance. It follows from the definition of capacitance. The capacitance is defined as the charge on capacitor divided by the potential difference between its plates. So this is the definition of potential difference. And the potential difference on the second capacitor will be given as the charge on the second capacitor divided by the second capacitance. And we know that while the plates move, everything changes here. The charges Q1 and Q2 change. The capacitances for C1 and C2 also change. But the potential difference here between these 2 points remains the same for both conductors. The potential difference on the first capacitor equals the potential difference of the second capacitor because they are connected in parallel. And so this is the first condition which we may write for the charges. The second condition is obvious. It follows from the law of conservation of electric charge. The charge cannot be created and it cannot vanish. So the total charge on the plates of the first and second capacitor, the total charge, it changes in time, it's a function of time, but the total charge on the upper plates must remain the same. It must remain the initial charge, Q, which is constant, which is just a number. It's given in the problem. It's given. So whatever changes in the charges on the plates of the first capacitor and the second capacitor, we know that the sum of these two charges remains constant and remains equal to the initial charge because of the law of conservation of electric charges. So we have another condition to solve this problem. Another condition is the law of conservation of electric charge, and this condition, which we have discussed, follows from the fact that the two capacitors are connected in parallel, and therefore the potential difference on the first capacitor is equal to potential difference of the second capacitor during the motion of the plates of the capacitor. At any moment of time, the potential differences are the same on both capacitors. So we have two equations, and from the second equation we can say that we can write that Q1 divided by Q2, Q1 divided by Q2 equals C1 divided by C2. So this is from this equation we can obtain. Well, do we know anything about the relationship between the C1 and C2, between the capacitances of these two capacitors? Yes, we know something about it. We know that the capacitance in general, we obtained this formula during last lecture, is equal to electric constant, the area of the plate of capacitor divided by the distance between the plates. By the distance. In our situation, the distance is a function of time, but the area of the plates does not change. The area of the plates does not change, only the distance changes. So in this formula, only the denominator is the function of time, while the numerator is constant. And so we can easily find this quotient, this relationship between C1 and C2. So C1 will be inversely proportional. So let's put it in this way: epsilon 1, the surface area divided by the distance of the first capacitor, distance between plates, and we divide it by the C2, which will be epsilon 0 area of its plates and distance between the plates of the second capacitor. And that will give us the area, and the electric constant will cancel. And what we have, the distance between the plates of the second capacitor, the function is given, it's d0 minus vt divided by the distance between the plates of the first capacitor, and this function is also given, it's d0 minus vt. So this is the relationship between the charges, actually, between the charges. And we have two equations, the first equation and the second equation, and two equations with two unknown quantities, q1 and q2. So if we have two equations and two unknown variables, we can always find these two variables if the equations are compatible, if they do not follow from one another. So we can take the q1 from the first equation and substitute it here to the first equation, and that will give us, instead of q1 here, I will take its expression from the second equation. That will be q2, and this quotient, which is d0 minus vt divided by d0 plus vt. So this is q1 obtained from the second equation, and I substitute this expression into the first equation, and so I will have plus q2 equals capital Q, which is given in the problem. And from here I can easily find q2. That will be capital Q divided by 1 plus this expression d0 minus vt divided by d0 plus vt. And after obvious simplifications, I will have q times d0 plus vt divided by, and here I will have 2 d0 minus vt. 2 d0, because 1 d0 plus 1 will give us 2 d0 minus vt. So and d0 plus vt minus vt. Vt will cancel, certainly. There will be no vt here. Just 2 d0 in the denominator. Plus vt and minus vt. They will cancel. So if I find the second, if I find the another charge q1 as a function of time, I will obtain similar equation, but obviously here will be minus Vt, so it will be capital Q d0 minus Vt divided by 2 d0. So I know, by solving the two equations, I know the charges on the capacitors at any moment of time. Any moment of time. This is time. So this is a function of each electric charge on each capacitor is a function of time, as we guessed. It's a function of time. And so the charge here changes. It's decreasing in time, because we have here minus t. And the charge on the second capacitor is also changing, but it's increasing with time. Increasing. And it's obvious that the amount delta Q, that is the charge which will flow from one capacitor to another, the amount of the delta Q, the charge lost by the first capacitor will be equal to the charge gained by the second capacitor. So the delta Q1 will be equal to, if we put it in time, it will be equal to Q capital Q V delta T divided by 2 d0. So from this formula I can obtain the change of Q1. This formula gives me this variable Q1, and the change in Q1 during small time interval delta t can easily be obtained here. The change will be defined by this formula, and it will certainly be equal to minus delta Q2, because delta Q2 will be the same but with opposite sign. Opposite sign. And so if we divide this formula by delta t, then we obtain the electric current which flows here, because by definition current is the charge that goes through the wire divided by delta time, by delta t, that is the time interval during which this charge went through this wire. So dividing the first formula by delta t will give us the final answer, which determines the magnitude of electric current flowing in this circuit. So that's the final answer to this problem. We needed to find electric current, and we have found it. The current will depend on the initial distance between the plates of capacitors and initial charge put here in this circuit, and the velocity at which the plates move. And we remember that the plates of the first capacitor were, the upper plate was moved upward so that the distance increased, and for the second capacitor the upper plate was moving downwards so that the distance decreased. And the velocity of motion of these two plates is given in this problem, and it's found here in this formula. The current which will flow from one capacitor to another capacitor is proportional to the velocity at which the plates of the capacitors move. So this is the final formula in this problem. This is the final answer to this problem. And now I will discuss what is known as Kirchhoff's laws or Kirchhoff's rules. Kirchhoff's rules, which allow to calculate currents and potential differences in any complicated circuit. Whatever circuit you have, whatever complicated connections. Kirchhoff's rules based on the laws of physics. It's not a law of physics. There are two rules discussed by Kirchhoff, a German scientist, and these two rules are based on physics laws, which you know. We will discuss them now, and these rules allow one to calculate currents and potential differences in any complicated circuit. So you may have a linear circuit containing some elements, arbitrary elements, arbitrary circuit. And you may have many other connections here. You may have anything connected in any point, and here you may have another connection, another thing, and here you may have another thing with different elements, and here you may have another thing connected here, etc., etc. Any complicated circuitry, arbitrary circuit, arbitrary, whatever circuit is there. It may be very large. It may be extended. It may be very complicated circuit. But there are two rules which allow one to calculate all the currents in any element, all the currents and all the potential difference on any element of this circuit here or here. If you know the elements of the circuit, that is, all the resistances are known and all the electromotive forces of the batteries are known, electromotive forces of all the batteries are also known, etc., etc. So if all the batteries are given, all the electromotive forces of all the batteries are given, and all the resistances are given, then the Kirchhoff's rules allow one to calculate anything in this circuit, all the potential differences between any 2 points, between these 2 points, for example, and this point, or potential or current in this element, etc., etc. So the first rule is based on the law of conservation of charges, and it says if there is a junction in the circuit, a junction is a point where several wires connect, then the current, electric charge is not accumulated in this point, and it's not lost in this point. The charge is conserved, and therefore the total charge which comes here to this point from different wires, there may be other wires here going. The total current which comes here, the total charge during some interval of time must be equal to the total charge which goes out of this point along other wires along the same period of time. So the total current going through this junction, through this point where different wires connect, the total current must be 0. So the current which is inflowing, let it be something like that, must be equal to the current which is outflowing, that is currents with other signs, that is other currents, etc. And the total algebraic sum of all the currents must be 0. The total algebraic sum. So the currents which flow here, if the current flows in the point, it's taken with the plus sign, and if the current goes out of the point, it's taken with minus sign. And the total algebraic sum of all currents going through this junction must be equal to 0. Why? Because the charge, the electric charge, is conserved. it's not accumulated in this point. And the total charge which comes here must be equal to the total charge which goes out of this point during a certain time interval. That is the first Kirchhoff's law, and this law must be applied to every junction in your complicated circuit, to every junction, every point where the wires are connected will give you an equation of currents. Well, if we don't know where the current actually flows, how can we decide whether it will be with the sign plus or minus sign? At first, originally, we assume that the currents flow in certain direction in each element of this circuit. We assume that the current flows here, and we assume that it flows here, and we assume that it flows here, etc., etc. We take each circuit, each element in this circuit, and we assume the direction of the current, and we denote this current by some letter or some index. It may be any index, 15, if we have 15 currents here. Then we just assume that the currents have some direction, and based on our assumption, we write down all the equations here in the Kirchhoff's law. And finally, when we solve these equations, if the current obtained as a solution is positive, then we were right in choosing the direction of current. If the current obtained from this equation as a solution of equations will be negative, then the actual current flowing through this element of circuit goes in the opposite direction, which makes no difference, no problem at all. We have chosen some direction of current, and actually the current turns out to be going in different direction. That's not a problem. The main thing is to find the magnitude of current and its direction, and everything will be found. Whether positive or negative will just indicate whether we have guessed correctly the direction of current, or if we have chosen an opposite direction, opposite to a real current. So the first Kirchhoff's law, the first one, is based on the law of conservation of electric charge. And the second law, the second Kirchhoff's rule, is based on the law of conservation of energy, actually. Conservation of energy. Let us take a small element, a small charge, delta Q, and let us imagine that we draw this, that we pull this charge along the circuit, along some closed part of the circuit. For example, along this closed part of the circuit. We pull this charge, and as we pull it in every element, we will have to perform some work in order to displace this charge against the forces of electrostatic forces acting on this charge. And so we will perform some work in each of the elements. And this work is given either by the electromotive force of the element or by the potential difference which falls on the resistor. Anyway, according to the Ohm's law, we know the potential difference on the resistor. It's equal to the current through this resistor, across this resistor, times the resistance. And we know the potential difference, so we know the work which we perform if we pull the charge across this resistance. And then we know the work which we will perform if we pull the charge through the some electric battery, if we know the electromotive force of this battery. Then if we pull this charge from the initial point along the closed circuit and finish at the same point where we started, then the total potential difference must be zero. The total potential difference must be zero, because the potential, electric potential at this point, it remains the same. And we started from here and we pulled the charge through all the potential differences, and we came to the original point, and the potential difference, the potential, electric potential here must be the same as it was when we started this trip of the charge along the closed circuit. So the fact that the potential difference is the same means that the work done in electrostatic fields, if we pull the charge along the closed circuit, the work is zero. It cannot be positive. It will be zero. If it's positive, then we will have the possibility to obtain infinite amount of work by just pulling the charge here in this circuit. But it's impossible. There is a law of conservation of energy, and we cannot obtain infinite energy from nothing. So if we allow this charge to travel along a closed circuit, then we start at some certain potential, electric potential in this point, and we end at the same electric potential. It means that the potential differences on all the elements in this circuit in total potential differences zero if we go along the circuit. So if we go along, we will take into account the potential difference of each battery as an electromotive force, and if we go from negative terminal of this battery to positive one, then the positive charge will be repulsed from here, from the positive terminal, and we will have to perform work. And so we may take this element as positive, and then if we take another element, and here again, and here we go from positive to negative terminals of this battery, then we take it with opposite sign, and this is, for example, no matter how you denote it. And then we go through the resistance, and if we know where the current flows, then we know where the plus and sign is, plus here and sign here, and again we will perform some negative work. If we move in this direction, that will be the current here in this element times the resistance, etc. We take all the potential differences on each element according to the Ohm's law, and then we take into account each electromotive force with appropriate sign. Whether we go from plus to minus, that will be plus sign, and if we go from minus to plus, that will give us minus sign. And as we know that the electric potential at this point will not depend on whether we have drawn the charge here or not, then that will be zero. The total potential difference along the closed circuit is zero. That is another condition of Kirchhoff's rule. And these two conditions will be written many times. The first condition will be written many times for each junction in the circuit, for each junction. And so the second equation will be written many times for each closed circuit in this, complicated circuitry, for each closed small circuit element, circuit section. So as many sections we have, 1, 2, 3, 4, 5, for example, then we will have 5 equations of the second type. And so we will have a system of linear equations, and the number of unknown variables in these equations must be equal to the number of the equations, and then in this case we can solve the system of linear equations and find all the unknown quantities, and unknown quantities will be the currents, the electric currents, which flow through each element of the complicated circuit. So this is just a theoretical approach to Kirchhoff's rules, and in order to apply these ideas, we will consider a small and simple problem. We will consider a simple problem, which will be problem 502. So we have such a circuit. EMF E1, the battery E1, the resistance R, and another battery which is E2, the battery with electromotive force E2, and so these are points A and B. So two cells or two batteries with electromotive forces E1 equals to 1 volt and E2 equal to 2 volts are connected as shown in this figure. The resistance R is given. It's 0.5 ohm. The internal resistances of the cells are the same and equal to 1 ohm each. So there is an internal resistance of each cell here and here. And this internal resistance is also given, and it's equal to 1 ohm each. Determine the currents flowing through the cells and the resistance R. Disregard the resistance of the feeding wires. Okay, so there is a current in this wire. Let's choose arbitrarily the direction. I don't know the direction. And let's denote this current by some letter, for example I1. And there is a current flowing here. Let's choose the direction, which seems to be correct, but I repeat, if the chosen direction is opposite to the real direction of this current, then what we will obtain will be just a negative value for this current. It's not a problem. So we choose the direction for the second current, and also there must be a current here, and we must find all these currents, I1, I2, I1 flowing here in this wire, and I2 flowing here, and I3 flowing the resistor R. We have to find all these currents in the problem. The circuit is rather simple. It's not a complicated circuit, and therefore the Kirchhoff's rules applied to the circuit will be very simple, will give us very simple equations. Well, the first equation for this junction of wires, the first equation will give us that the current I1 taken with the plus sign as it goes in this point, plus again with the plus sign the current I2, minus the current I3, we take it with minus sign because it flows out of the circuit, out of the junction. All this must be equal to 0. I repeat you why, because there is a law of conservation of electric charge. And so the charge is not accumulated at this point, and so all the currents going in must be equal to the sum of currents, the total currents going out. So this is just an example of the first Kirchhoff's rule. The total current in this junction is 0. If we write similar equation for the second junction, we will obtain the same equation, the same. So there is no point to write another equation for point B. It will be just the same. And that's the general rule. You don't have to write this equation for all the junctions in the circuit. Actually, the number of equations must be less than the number of junctions, because at least one equation will be a consequence of all other equations. Now the second Kirchhoff's rule, we must take a closed circuit, for example this one, and calculate all the potential differences along this circuit. All the potential differences, if we go this circuit in this direction, in the direction of the current. So the potential difference on this element will be the current I3 times the resistance R. That will be the potential, that will give us, according to the Ohm's rule, that will give us the potential difference here. And as we go along this closed circuit, we will obtain that here we will move the positive charge against the internal field in this battery. So that will be minus, that will give us minus E1, and that will be 0. I have forgotten already about the internal resistance here, and the internal resistance will give us again plus the current here is I1 times small r. That will give us 0. So we must take all the potential differences on all the active resistances, including the internal resistance of the battery. And if the current goes in the direction of our circular trip around this element, then we take the potential difference with the plus sign. If we go from against the electric field inside the battery, then that potential difference will come here, will be included with minus sign in this equation. Now let's take another equation, for example, for this section, for this cell of the total circuit. And this will give us, if I go from positive to negative part inside the battery, that will give me a plus sign of the battery E2 with electromotive force E2. Then I go from negative, then I go against the current I2 on the internal resistance. That will give me minus current I2 internal resistance of the battery. And then I will go against the current I3 in opposite direction. The current flows from A to B, and I trip along this circuit, closed circuit, from B to A. So it will be minus the current in this section I3 times R. That is, the second Kirchhoff's rule will give me two equations related to this circuit, closed circuit, and this closed circuit. Certainly I can choose another closed circuit here, but that will give me no more information, because another closed circuit consists of these two closed circuits, and the equation for another for the total closed circuit will be a consequence, just an algebraic consequence of these first two equations. So I have three equations, a system of three simultaneous equations, and three unknown quantities, I1, I2, I3, the currents in three sections of this circuit. Therefore, I can certainly find all these unknown quantities as currents. It's here, and it's here, and also here and here. And you know how to solve the system of simultaneous equations. This is not physics, this is mathematics. Physics has ended as far as we have completed these simultaneous equations. So when do we have physics in this problem? When we analyze the situation, and when we apply laws of physics, and when we write down the laws of physics in the form of equations. As far as we have written the equations describing all the processes in this linear circuit, as far as we have completed the equations, on this point physics ends and mathematics begins. And now this is not physics, this is just a mathematical problem to solve a system of three simultaneous equations and to find three unknown variables which are found in these equations. This is a mathematical problem. I will not waste my time on this problem. You can do it yourself. It's not a complicated situation. You can do it yourself. I will not waste my time on this mess. But I will remind you, yes, there is a good question. Do Kirchhoff's laws work in all cases? No. No, certainly not. As any law of physics, any rule of physics has, any rule in physics has a limited domain of applicability, and the same is true for Kirchhoff's rules. Kirchhoff's rules work only when you have steady currents, steady direct currents in your circuit. If you have alternating currents, then the Kirchhoff's rules, strictly speaking, do not work. But they can be anyway applied in the case when the frequency of the current in your alternating current circuit is small, so that the wavelengths corresponding to this frequency, wavelengths of light, radio wavelengths corresponding to the frequency of the alternating current, is much larger than the dimensions of this circuit. If the dimensions of the circuit are, say, 1 meter, then any radio wavelengths larger than 100 meters may be considered much larger than the dimensions of the circuit, and 100 meters is about 1 megahertz or 3 megahertz. So up to 3 megahertz in this case, alternating current, you can use the Kirchhoff's laws. But if the frequency is much higher, if it's like gigahertz, the Kirchhoff's laws will not work, certainly will not work, because they were obtained only for static currents, only for direct currents. So, as far as magnetic fields are concerned, we will discuss magnetic fields during next week, our next week lectures. And now the time is over and we have to finish this lecture. Thank you all and goodbye till next time.